Welcome back to the session, and today let us see the types of functions. So in the previous video lecture we have seen what is a function. I'll just recall that. So a function means it will be from a domain set to a codomain set, and every element in the domain will be uniquely associated to the codomain element. So that is a function. And also I have given you a very good analogy that you have a domain set to be as children and codomain set to be as girls, and the function here it will be mother. So which means that in the domain set we have children, so each and every children will definitely have a mother, so therefore it will be associated, and no children will not have a mother. So in that case none of the elements in the domain set will be left free. This is all about the function. And today let us see the types of functions. So we have got many types, of which we'll see a very few. First type, it is one-to-one function, or we call it to be as a injective function. And second function is onto function, or we call it to be as a surjective function. The third one, it is a bijective function. So now let us see how we'll make a difference between all these types of functions. So types of functions. First type we have is injective, that is one-to-one function, or otherwise it is called as injective function. So how we define? Normally to define a function, definitely we need domain set and codomain set. As I have said already, domain set, it will consist of all possible values of input, and this range or codomain set, it will have the possible output values. So here one-to-one, suppose if this is my domain set X and if this is my codomain set Y, and we'll have a function from this X to Y. So now this function f from X to Y is said to be one-to-one or injective if each and every element is distinctly mapped onto each and every element of Y, right? So which means that, again I repeat it, the function f from X to Y, that is the domain set X to the codomain set Y, is said to be one-to-one if all the distinct elements of X are distinctly mapped onto Y. So this is called as the one-to-one function, right? Look at this now. See, each and every element is distinctly mapped onto the elements in Y. So this is called as an injective function. Now these are called the images of X, or we can also say that these are called as the pre-image of the elements in Y. So this is how we define a one-to-one function. Or there are many ways in defining one-to-one function. So when you go for the GATE class or competitive examinations, and if you are asked to find out one-to-one, in that case you need not do this way, it will be a lengthier one, and in that case you have many ways to find it. So next is the other way, we can say that is if we assume that f of x1 is not equal to f of x2, so this should imply x1 is not equal to x2, which means that f of x1 is an element in the domain set, and this will be mapped onto the codomain set under the function as f of x1. So you can also say that a function is one-to-one if f of x1 is not equal to f of x2, implies x1 not equal to x2. Or this is also equivalently saying that f of x1 is equal to f of x2, implies x1 is equal to x2. So this way also we can define a function to be as one-to-one. Or the other way is that, suppose if a function is given, right, if f of x is a given function, then in case if we are supposed to find out whether this is a one-to-one function or not, we will have to find out the derivative of this function f dash of x, we will have to find it. if f dash of x, right, so if f dash of x exists, say for a given interval or for a given set, if suppose if this is greater than 0 or if it is less than 0 na, then the function f is said to be 1 to 1, right. This is also the other way of defining a function to be as 1 to 1. Suppose if a function is given and if you are finding out, this is the very easiest way one can do it when you go for the higher competitive examinations. So f dash of x, you will have to find it. If that f dash of exists na, then you will have to see to that if any interval is given, if it is either greater than 0 or less than 0. So if it is either greater than 0 or less than 0, then you call it the function to be as 1 to 1. And so here moreover specifically we can say that whenever it is greater than 0, it is monotonically increasing function, and whenever it is less than 0, we say it to be as monotonically decreasing function. Suppose in case if our f dash of x at times in a given interval, if it is less than 0, at times, right, at times within the given interval, and at times if it is greater than 0 within the given interval, then it is said to be not 1 to 1, right, understood. So the function is f is not 1 to 1. So one thing is whenever we find out the derivative and if it exists, and more specifically if an interval is given or if the range is given, we will be finding out whether it is greater than 0 or less than 0, the derivative. So if it is that na, then we will say it to be as 1 to 1. And moreover specifically whenever your f is 1 to 1, that is if it is greater than 0 over the given range, then it is said to be monotonically strictly increasing function. Then if it is less than 0, we say it to be as monotonically decreasing function. So we can also say that strictly increasing, strictly decreasing. And next is whenever your f dash of x is less than 0 at times, that is for a given interval, if to certain extent if I have less than 0, that is negative value f dash, and to certain extent if I have f dash to be a positive value, and at times if I have it to be as equal to 0, in all those cases I call a function is not 1 to 1. So this is all about a 1 to 1 function. And next we have onto function, right, onto function. So onto function is otherwise called as surjective function. So how do we define this onto or surjective function is, again I'll have a domain set x, I'll have a codomain set y, and we have a function f here. So here I'll have the elements in my domain set. Likewise, I'll also have elements in the codomain set. So now the function f from x to y is said to be onto. There are many ways of saying, right, is said to be onto. That is for each and every element, right, for each and every element of y in my codomain set, there exists an element x in the domain set capital X such that f of x is equal to y. So this is one way of defining the onto function. Let me recall this. A function f from x to y is said to be onto if for every element of y in y there exists an x in x, such that, which means that for each and every this element, right, for each and every y in y there exists an x in x such that f of x is equal to y, then we call it to be as onto function or surjective function. The other way of defining onto function is that the function f from x to y is said to be onto if the range of f, this is other way of defining, if the range of f is equal to y. Y is nothing else but the codomain set. So whenever the range of y is equal to the codomain set, then also the function is said to be onto. So there are two ways we can define an onto function. So we know what is a range. So range, it is nothing else but the output, all the output values of the given function. Y here, it is a codomain set. So look at this na. So here the range is nothing else but what? ABC is the range. As well the codomain is also ABC. So whenever my range is equal to the codomain, then the function is said to be onto. So this is other way of defining a function to be as an onto function. And next is bijective. So next is bijective. So when do we say that the function is bijective? So whenever the function f from x to y is both 1 to 1, right, both 1 to 1 and onto, then it is said to be a bijective function. Or moreover, I can say that for each and every element of x, if it is exactly mapped onto the element of y in the codomain set, then we call the function to be as bijective. So in short, I can express that function to be as both 1 to 1 and onto to be a bijective function. So this is all about the types of functions, right? Okay, now here we have few examples, like a function will be given over a range, that is the domain and codomain. We will have to say that whether a function is 1 to 1 or not 1 to 1, right? So all these problems are pertaining to 1 to 1. So that is, we call it to be as injective function, injective function. So now here we have a function f from -1 to +1, that is open interval. Open interval in the sense, this -1 and +1 will be excluded, and in between -1 and +1 only I will have the domain set. And my codomain set is set of all real numbers. R stands for real numbers. And the function is defined to be as f of x is equal to x square plus 2x. So now that we will have to check out whether this is an 1-to-1 function or not. So how do we check it? I have given you many examples, so many ways of finding out. So the one of the easiest way is that, let me find out what is my f dash of x, right? Let me find out what is my f dash of x. So now what is your f dash of x here? Differentiation of x square with respect to x, we get it to be as 2x, plus differentiation of this 2x with respect to x, we get it to be as 2. And within this range, I will have to see whether it is greater than 0 or less than 0. So if it is throughout that range, if it is greater than 0, or throughout that range, if it is less than 0, then I say the function to be as 1-to-1 function. And more specifically, I can also say that it is whether a strictly increasing function or a strictly decreasing function, right here. So now f dash of x is equal to 0. Now what is my domain set? So here I have a number line system. So this is from codomain is, here I have -1 and here I have +1. The entire range is from negative infinity to positive infinity. So now if the next value I can take, right? So for simply if I take x is 0 here, say, right, x is 0 now, I'll have what? I'll have to substitute. When I substitute x is equal to 0, 0 lies between -1 and +1. So whatever value I take between this, that should be mapping on to each and every numbers which is real. So if that is so, and then I can say that it is 1-to-1 function or not. So if I substitute x equal to 0 now, I get f dash of x to be as 2 into 0 plus 2, which is greater than 0, right? So that is equal to 2, I get it to be as greater than 0. Next, even I can take it to be as -0.5, right? If I take x to be as -0.5, then I will get it to be as 2 into -0.5 plus 2. So 2 into -0.5, I'll get, this is 1 by 2, so this I get it as -1 plus 2, which is equal to 1, again that is greater than 0, right? So now within this range, so whatever thing I get it, everything I get it to be as greater than 0 only, of course that is in my real number. So therefore this is greater than 0, and the function f is said to be a 1-to-1 function. So since because it is strictly greater than 0, I can say that it is strictly monotonically increasing function. So this is how one will be finding out whether a function is 1-to-1 or not. And next I have a function g from 1 to infinity, which means that the domain set takes an element from 1 so on till infinity, and it should map with all the real numbers here. So the function is defined to be as g of x is equal to e raised to the power of x cube minus 3x plus 2. Let us see here. Let me first find out what is my g dash of x. So g dash of x is equal to e raised to the power of x cube minus 3x plus 2 into, I'll have to differentiate this. So 3x square minus 3 plus 2 differentiation becomes 0. And next is what it says here, we'll go for the number line. So it says that from 1 to infinity. So let me take 1 over here and positive infinity. The interval is this and it has to map for the entire real numbers. So let us check now. So let me take x is equal to 2 somewhere here, right? So if I take 2 now, my g dash of x, what it happens? G dash of 2 will be equal to e raised to the power of 2 cube minus 3 into 2 plus 2 into 3 into 4 is 12, 12 minus 3 I will get, right? E raised to power of all the positive numbers, we do get it as positive, this is positive, and 12 minus 4 it is again a positive number, so I get it to be as greater than 0, right? So whatever number I take within the positive range from 1 to infinity, right now, so e power this becomes positive and this also becomes positive. So therefore this becomes, that is g dash of x for the interval 1 to infinity, it all gives me the real number and this is greater than 0. So if this is greater than 0 now, then I can say that g is 1 to 1. So since because it is greater than 0, I can say that it is strictly monotonically increasing function, and the next function we will have h from real numbers to real numbers. Real numbers to real numbers now I can take from negative infinity to positive infinity, and my h of x is given to be as 2 raised to the power of, so this I can write it to be as 2 raised to the power of x square minus x, right? So we will find out what is our h dash of x. H dash of x, so it is of the form a power x. Whenever we have a power x, this upon differentiation, I will get it as a power x into log a into the differentiation of x becomes 1. So like way if I differentiate it, this becomes 2 raised to the power of x square minus x, right? And into log 2 into the differentiation of this becomes 2x minus 1. So this is the differentiation. And now the number line, the function says it is from a real number to a real number, which means that it ranges from a negative infinity to a positive infinity. So now with this I will have to check out whether this is a one-to-one function or not. So for which I can take any random number, right? So I can give any, so let me take it to be a 0 first, right? So if I substitute x as 0 here now, I will get 2 raised to the power of 0. Anything raised to the power of 0, it is 1, which is a positive. So here in this case, I do get it to be as a positive value. So this becomes positive. And of course, log 2 will also be a positive value. Here you substitute now, x is equal to 0 if you substitute, what do you get? 2 into 0 becomes 0, 0 minus 1, here I get it as negative. So product of 2 positive with 1 negative, I get only a negative number, right? So my h dash of 0 will be less than 0, right? In this case, when I take my x to be a 0, then my h dash of 0 will be less than 0. But in case, suppose if my x is equal to half, say, what do I get, right? Half now, what do I get? Or if it is less than half now, what do I get? I will have to discuss now. So again, if it is half now, this becomes positive, this also becomes, log 2 is always positive. So these two numbers will be positive. I will have to check only for this number. Suppose in case, if this is not equal to 0 now, I will have 2x is equal to 1, not equal to 1, and x is not equal to 1 by 2. Other than 1 by 2, if I take any number, what do I get, right? If I take 1 by 2 first, let me check out that. So if I take x is equal to 1 by 2, my h dash of 0, I will have positive, right? I will have positive, then this number, when x is equal to half now, 1 by 2, 2 and 2 will get cancelled, 1 minus 1, I get it to be a 0. So this it becomes 0. And next is I can take other value, right? Say for example, if I take it to be as 3, right? If my x is equal to 3, so that is also a real number. So in this case, h dash of 0 will be, this term it will be positive, this also it will be positive, and the last one if you see now, it will be what I substitute 2 into 3 is 6, 6 minus 1, that becomes positive. So therefore this will be greater than 0. See here, so I have one value less than 0, one value equal to 0, and for one more value I get greater than 0. So which means that here it keeps oscillating. At times it is less than 0 over this range of set of all real numbers. At times it is equal to 0, at times it is greater than 0. So therefore I say that since because my h dash of x is at times less than 0, equal to 0, greater than 0, I will conclude that my h is not 1 to 1, not 1 to 1. So this is how we will be checking out whether a function is 1 to 1 or not 1 to 1. Okay, back to the session, and we will see how the function is 1 to 1, on to, or bijective, or even how to find out the composition of two functions. So yesterday we have seen, or in the previous lecture we have seen how to define a composition of two functions, right? So suppose in case f is a function from a to b and g is a function from b to c, then the composition of f and g will be a function from a to c, that we have defined it, and then it is defined to be as g composition f is equal to g of f of x is a domain here. So using that we will try to find it. So now here we have a function f from r to r and g from r to r are functions defined by f of x is equal to this, right? F of x is defined to be as x square plus 3x plus 1, and g of x is defined to be as 2x minus 3. And with this we are supposed to find out the composition of f and g either way, right? So first is we are finding out composition of this g composition f of x, since because we have got x here. So the definition of composition of two functions says that g composition f of x is f of g of x. So now I will have to find out what is my this f of what is my g of x. G of x is given to be as 2x minus 3, and now what is my f of x? In the place of x I have got 2x minus 3, so which is equal to, I can again substitute that in the place of x, 2x minus 3 the whole square plus 3 times of x I have here, it is 2x minus 3 plus 1, so which is equal to 4x square plus 9 minus 12x plus 6x minus 9 plus 1. So that is 4x square minus 6x plus 1 will be the composition, right? F composition G will be this. And in a similar manner, we will find out what is G composition F. So G composition F is equal to F of G of this will be G of F of x. And this is G of f of x is what here? We have x square plus 3x plus 1. So that is g of x now, it is 2 into x square plus 3x plus 1 minus 3. So that is equal to 2x square plus 6x plus 2 minus 3, or that is equal to 2x square plus 6x minus 1. So now f composition G is this and G composition F is this. And the next one we have f from R to R and G from R to R are defined as f of x is equal to x square minus 2 and g of x is equal to x plus 4, and we are supposed to find G composition F and F composition G. So this composition of two functions, I hope you can do it since we have done the previous problem. Now we will do only this, we will check out whether the functions are injective, surjective or bijective. So that part alone we will do it now, and this part later on you can just have a look at it and then you can work out the problem. So now we have f of x to be as x square minus 2 and g of x to be as x plus 4. So now that to find out 1 to 1 we will have, right. So to find or to prove or to check whether f is 1 to 1. Let us check out whether our f is 1 to 1. The other way we will do it. So, one way what we have done is that we have found out the derivative, and once if it is a positive or greater negative, we have decided that f is 1 to 1, and also we have said that it is monotonically strictly increasing and monotonically strictly decreasing. Suppose at times if it is less than 0, or if it takes positive value, or if it is equal to 0 within that given range, then we say that function is not 1 to 1. So, the other way what it says is that, suppose if we consider, that is, let f of x1 or f of x is equal to f of y. So, if it is 1 to 1 now, we should be finally arriving that x is equal to y. So, which means that each and every element of your x is distinctly mapped onto y elements, right. So, f of x is what here, x square minus 2, which is f of y na. So, in the place of x you replace it y square. So, minus 2 will go off. I will get x square is equal to y square, or my x will be equal to plus or minus y. See here, I have got this x is mapped onto y as well as onto negative y. So, therefore, it is not 1 to 1, right. F is not 1 to 1. F is not 1 to 1. Let me give you an illustration of this, right. So, I have x, I have y, right. No, f it is a function from R to R, right. F is a function. Then you see here, I have an element as x, right, and that is mapped onto positive y as well as negative y. So, now this x is mapped onto y as well as onto negative y. So, that is not in case of my 1 to 1. So, what does 1 to 1 say? Each and every element of my x should be distinctly mapped onto the elements of y. That is not possible. So, therefore, we say that f is not 1 to 1. So, this is other way. By just looking into this, I can say that. And next is to prove that f is onto, or f we will have to check out whether it is onto or not. So, for onto, what way we have defined the onto function? So, for every element of y in the codomain, there should exist an x element in the domain set such that my f of x is equal to y, right. So, let me see. So, what is all about the function here? Function is from set of all real numbers to real numbers, and here this is my codomain, this is my domain. So, now see here, for every element y belonging to R, this y belonging to R is the codomain set, right. That is my codomain set. There exists an element x belonging to R which is a domain, right, which is a domain set such that we have f of x is equal to y. I will have to check out. So, whether that also belongs to a real number or not. My f of x is what here? X square minus 2 is equal to y. So, now you try to find out what is your x. So, x square will be equal to y plus 2, or your x it will be equal to plus or minus square root of y plus 2, right. So, now for every element y belonging to a real number codomain, right, I should try to prove that my x also belongs to this codomain set, which is set of all again real numbers. Let me check out now. Suppose for example, if my y is equal to, right, if my y is equal to say 0, I will get root 2, that will be a real number. Suppose if I take a negative value, no? So, if y is equal to minus 3, so minus 3 plus 2, I get it to be as root of minus 1, which is I, which is a complex number. So, this does not belong to. So, here if y is equal to minus 3 now, I will have x is equal to plus or minus root of minus 1. So, in that case, it becomes a complex number, but it does not belong to a real number. So, therefore, f is not onto. Understood? Since because f is not 1 to 1, as well it is not onto, we can say that f is not bijective. F is not bijective. So, bijective only if the functions are 1 to 1 and onto, we say it to be as bijective. In this case, it is not. So, therefore, it is not a bijective function. So, next we will have the function g of x is equal to x plus 4, right. So, g of x is equal to x plus 4. I will have to say whether this is again a one-to-one or onto function. How do we check it out? In a similar manner, we will do it, right? So, let us assume that what is G function first of all? G is a function from set of all real numbers to real numbers. So, let G of x is equal to G of y. So, if I am able to show that my x is equal to y at last, then the function becomes an one-to-one function, right? So, G of x, now what is my G of x? It is x plus 4. That is equal to y plus 4. So, now x is equal to y. So, see here, each and every element of my domain set has been distinctly mapped onto my codomain set. So, therefore, so this implies x is equal to y, yeah? G is 1 to 1. So, the other way also I can say, so here I have x, that is set of all real numbers to real numbers. G is a function. I have x, whatever element I take, it is distinctly mapped. So, it is distinctly mapped. So, therefore, G is 1 to 1. And next, how to prove that it is onto? So, for onto, to prove that G is onto, right? To prove that G is, or to check is G is onto, how it is defined is that for all y belonging to real number, that is the codomain set, you must be in a position to differentiate between a domain set and a codomain set. The second set becomes the codomain set and the first set becomes the domain set. There exists an element x belonging to this R, which is a domain set, such that your G of x is equal to y. So, G of x is what here? X plus 4. So, x plus 4 is equal to y. So, find out what is your x. X is equal to y minus 4. So, for each and every real number y, I will have to prove that x is also belonging to a real number. Let me check out now. Suppose if my y is equal to 4, say, what do I get? In this case, my x will be equal to 0, which is a real number, of course, in that case. So, we will have to check out for each and every value, at least for few values of y we will check out. So, now this, suppose if y is equal to, I have 3 now, so this will imply x is equal to 3 minus 4, which is equal to minus 1, which also belongs to a real number. And next, suppose in case if I take y to be a negative number, say minus 2. So, if I will get x to be equal to minus 2 minus 4, which is equal to minus 6, that also belongs to a real number. So, therefore, whatever y value I take which belongs to the codomain set, that is a real number, I do get again a real number which also belongs to R. So, therefore, my G is onto. Understood now? So, because my G is 1 to 1 and onto, I can say that G is bijective. I can say that G is bijective. And the next problem we have is, suppose f is a function from, right, R to R again, where f of x is defined to be as x square minus 11, and we will have to check out whether this is 1 to 1, onto or bijective. We will have to justify. Let us see, So, in case if I am supposed to prove that f is 1 to 1, how do I prove it? So, you can take, let f of x is equal to f of y. So, this should finally implies that x is equal to y. Let us check that. X square minus 11 is equal to y square minus 11. Minus 11 and minus 11 will go off. I will get x square is equal to y square, or my x will be equal to plus or minus y. See here, this x has two images. One is positive y, the other one is negative y. So, therefore, f is not 1 to 1 in this case. And also we will check out whether this f is onto or not. How do we check it? For that, we will take for every y belonging to the codomain set R, there exists an element x belonging to R. This we should prove such that our f of x is equal to y. So, what is our f of x? Our f of x is x square minus 11 is equal to y, or our x square is equal to y plus 11. So, x is equal to plus or minus square root of y plus 11. Now, for each and every real number, I do have to check out whether I get a real number again for x or not. So, now suppose in case if y is equal to 0, my x will be equal to plus or minus root 11, which belongs to a real number. Again, if y is equal to 12, say, minus 12 I can take. Negative 12 if I take it, I will have x is equal to plus or minus root of minus 12 plus 11, I get minus 1, which does not belong to real number. It is of course a complex number. So therefore in that case x will not belong to a real number. That is in case if I take my y to be as negative 12. So therefore my f is not onto. So since because f is not onto and 1 to 1, f is not bijective. So this is how one should be proving that whether a given function is 1 to 1 or onto or bijective. See again here the set S is given to be as 1, 2, 3, 4, 5 and 3 functions f, g and h are defined from the set S. S is nothing else but I have got 5 elements to S are given by this, and we will have to verify whether our f composition G is equal to G composition F and so on. So let me do that. So first thing we will go by A subdivision. So f composition, I will do one elaborately, the other things we will just rush it up. So we will find what is this composition. So for each and every element of S, F, G, H are what? It is from S to S. Yes, I have got this. So this how do I define? I will have to find out what is the composition of these two functions of an element 1 in S. So that is how it will be defined, f of G of 1. Right. So f of what is G of 1? 1, how it is mapped under G? 1 is mapped onto 3. So now what is f of 3? So f of 3 it is mapped onto 4. Right. Likewise, I will have to find out for all the elements. So this is what f of G composition, this is G of 2, which is f of G of 2, how it is mapped? 5. What is f of 5? F of 5 is 3 here. And likewise, f composition G of 3, that is f of G of 3. So G of 3, how it is mapped? It is 1, that is f of 1. So f of 1 under the function f, it is mapped onto 2. And f composition G of 4, so this is f of G of 4. So which will be equal to f of G of 4, how it is mapped? It is mapped onto 2. So f of 2, how it is mapped? 1. Right. And f of G composition, f composition G of 5, it will be equal to f of G of 5. So this is f of, how this 5 is mapped under G? It is mapped onto 4, and how this 4 is mapped onto f? So it is mapped 5. So now my this composition, that is G composition F, will be, I will write in terms of ordered pairs, right. So it is 1 is mapped onto 4, 2 is mapped onto 3, 3 is mapped onto 2, 4 is mapped onto 1, 5 is mapped onto 5. So this is how we will find out F, G composition F. Again we will find out what is F composition G. So that we will try to do it with a shortest way, right. So for each and every element I will have to find, no, I will have to see. So this is what G composition F of 1. So f of 1, 1 how it is mapped? It is mapped onto 2, and 2 how it is mapped here? It is 5. This way we will write. Again f of 2, 2 is mapped onto 1, 1 is mapped onto 3, so it is 2, 3. And 3 how it is mapped? 4, 4 is mapped onto 2, so therefore 3, 2. And 4 how it is mapped onto 5, 5 is mapped onto 4. So 5 how it is mapped? It is mapped onto 3, and 3 is mapped onto 1. So this is how we will find. So we have to verify whether F, G composition F and F composition G are one and the same. Check it out now. I have 1, 5, 1, 4. So therefore this is not true here. F composition G is not equal to this. And next is explain why F and G have inverses but H does not. So before that we will have to see what is an inverse function. So inverse function, what it says is that let F be a function from A to B. So this is inverse function. Alright. So f be a function from A to B and G be a function from B to A. Then this G is called as, the inverse of the function f, right. G is the inverse of the function f if it satisfies the condition G composition, that is G composition F is equal to IB, and I have F composition G is equal to IA. If it satisfies this condition, then we say that the function is an inverse function, right? So domain and codomain will be reversed. So now by knowing what is an inverse function, we will have to explain why F and G have inverses but H does not have. See here, no, we will just try to have. This is B subdivision we are having here. So F function, G function as well as H function we are supposed to prove, right? So this is my F function from S to S. This is my G function from S to S. This is my H function from S to S. So I do have 1, 2, 3, 4, 5 elements in my domain set of the function F. And how all these mapped? One is mapped onto, again I have the same elements now, so I'll write it. Then how it is mapped, I'll have to show it. So 1 is mapped onto 2, 2 is mapped onto 1, 3 is mapped onto 4, 4 is mapped onto 5, 5 is mapped onto 3, right? So for time being you just keep it aside. Coming on to this point, so I have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, right? So how is this G mapped? 1 is mapped onto 3, 2 is mapped onto 5, 3 is mapped onto 1, 4 is mapped onto 2, 5 is mapped onto 4, right? And again here 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So now 1 is mapped onto 2, 2 is mapped onto 2, 3 is mapped onto 4, 4 is mapped onto 3, 5 is mapped onto 1. See, now we are in a position to say why this F and G have inverses but H does not. So inverse function, we know that what? F from A to B and G from B to A, then this G will be called as the inverse of F if it satisfies this condition. Or the other way also I can write it. The inverse of this I can write it to be as what? F inverse of F of X is equal to Y, I can write it, right? That way also, sorry, this F of X is Y, F inverse of Y, I'll write this to be as X, that is equal to X. Now look at this, each and every element, right, each and every element is distinctly mapped and none of the elements here in my codomain set are left free. So therefore it is, now by saying the inverse function we can also say that whenever the function is a bijective function, then it becomes an inverse function, right? That way also we can say F inverse of F of X is equal to X. So now here that is true, and here again this is also true, but then here you see, this H of 1 is mapped onto 2 and H of 2 again mapped onto 2. So here what do we say? H of 1 is equal to H of 2. This implies that 1 is equal to 2, but it is not true, but 1 is not equal to 2. So therefore H does not have the inverse. H does not have the inverse. Whereas here each and every element is distinctly mapped and these two have inverses. That is why H does not have the inverse here. And next, C subdivision, we will have to find out what is F inverse. So F inverse, what did I say? If F has a function from A to B, then G becomes the inverse of A if it is from B to A. So now look at here, F inverse, it is from S to S. Again F inverse will be same S to S. I will have to reverse this order. 2, 1, 1, 2, 4, 3, 5, 4, 3, 5 will be my F inverse. And what is all my G inverse? G inverse will be, right? So 3, 1, 5, 2, 1, 3, 2, 4, 4, 5. So that is my G inverse. And next we will have to prove this. So D subdivision is, we will have to prove this. So G composition F the whole inverse. We have got this whole inverse, we will have to reverse this. So that is 4 comma 1, this is 3 comma 2, that is 2 comma 3, 1 comma 4, and then 5 comma 5 we have here. And next we know what is G inverse, also we know what is F inverse. We will find what is F inverse composite G inverse. So that is F inverse composite G inverse of 1. So again we will rush it up. So how the F inverse of 1 is mapped onto 2. So G inverse of 2, how it is mapped? This is mapped onto 4. So I will have to see. So this 1 is mapped onto 4. Again 2, it is mapped onto 1, and 1 is mapped onto 3. Likewise here 3, it is mapped onto 5, and 5 is mapped onto 2. Again 4 is mapped onto 3, and 3 is mapped onto 1. Then 5 is mapped onto 4, and 4 is mapped onto 5. So this is my G composition, G inverse composition F inverse. I will have to check it now. So now 4 comma 1, yes, I do have 4 comma 1, right? 4 comma 1, 4 comma 1, 3 comma 2, I have 3 comma 2, 2 comma 3, 2 comma 3, 1 comma 4, 1 comma 4, 5 comma 5, 5 comma 5. So now you will have to prove that this is not equal to, that also we will check it out. So this G inverse composition F inverse, we will have to see here from G inverse to F inverse how this 1 is mapped onto 3, and 3 is mapped here onto 5, and 2 is mapped onto 4, 4 is mapped onto 3. So 3 is mapped onto 1, 1 is mapped onto 2, and 4 is mapped onto 5, 5 is mapped onto 4, 5 is mapped onto 2, and 2 is mapped onto 1. So look at here now. So definitely that is not equal, see everywhere. So therefore this is proved. Now we have seen what is a composite function, how to find out the composition of any functions from a given domain to a codomain set. So by knowing the composition of any two functions, now we will have to, suppose in case if we have a function with unknown values, how do we find out those unknown values whenever the function are composite functions? So if that is so, now how do we do it? Let us see an example. So f and g are functions from real number to real number, where our f of x is defined to be as ax plus b, and g of x is defined to be as 1 minus x plus x square, and g composition f of x is defined to be this, and with this we are supposed to find the values of a and b. So now what is this given as f composition g of x? It is given to be as 9x square minus 9x plus 3. So how we define this function? That is g of f of x is equal to 9x square minus 9x plus 3. So g of f of x is what here? Ax plus b, that is equal to 9x square minus 9x plus 3. Now g of x, how it is defined? So it is 1 minus x here is ax plus b, plus x square is ax plus b the whole square, that is equal to 9x square minus 9x plus 3. So that is 1 minus, expand this, a minus x minus b plus a square x square plus b square plus 2abx is equal to 9x square minus 9x plus 3. So with this we are supposed to find out values of a and b. So now I can equate the like terms, that is by equating the coefficient of x square on either side, right? By equating the coefficient of x square on either side, I get a square is equal to 9. So which will imply a is equal to plus or minus 3. So next is I can equate, that is coefficient of x terms. Equating the coefficient of x terms, I have minus a here, I have plus 2ab, that is equal to coefficient of x here is minus 9. So I do have both the values. Again I will equate the constant terms. So when I equate the constant terms, I have 1 minus b plus b square is equal to 3 here, or my b square minus b minus 2 will be equal to 0. I will have to solve this. So, that is what b square minus b minus 2 equal to 0. Now, my b will be equal to 1 plus or minus root of this is 1 minus 4ac plus 4, that is 8 divided by 2. So, which is 1 plus or minus 3 divided by 2, which is equal to 1 plus 3 is 4, 4 by 2 is 2, 1 minus this is minus 2 and this. So, the values of A is plus 3 minus 3 and the values of B are 2 and minus 1. So, this is how we will be finding out the unknown values whenever a composite function is given over the defined codomain and domain set. So, next we have show that the function f of x is equal to x cube and g of x is equal to x raised to the power of 1 by 3, where x belongs to set of all real numbers are inverse of each other, which means that we are supposed to prove that f and g are inverses of each other. So, what does that definition say for inverse? So, f definition says that if f from, so here it is domain is R, f from real number to real number, then g from this real to real is inverse, then your f composition g should be equal to the I of R, or g composition f is equal to I of R. If from this I can say that f is equal to g inverse or g is equal to f inverse. So, if I could arrive this now, then they are inverses of each other. So, let me take now, I will consider or I will find what is f g composite f of x. So, this is f of g of x. So, this is f of g of x is x raised to the power of 1 by 3. So, this is f of x is this. So, therefore, it will be x raised to the power of 1 by 3 the whole cube, which is equal to x. This I can write it to be as ix, identity, where I is nothing else but identity. So, identity into any element will be that element. So, upon cancellation I get f composition g is equal to I. So, from here I can say that f equal to g inverse. Again, on the other hand, we will find out what is f composite g. So, this is g of f of x. So, that is g of, what is f of x here? It is x cube. So, that is equal to x cube whole raised to the power of 1 by 3 is my this. So, that is x, and this can be written as ix, and this is g composition, f composition g is equal to I. So, from here I can say that my g is equal to f inverse. Look at these two statements, f is equal to g inverse, g is equal to f inverse. So, therefore, both f and g are inverses of each other. Thank you.